Hello, and welcome to Math with Mr. Bill. I'm Bill Anderson, and today we're going to be discussing a function and its intervals of increasing and decreasing, where it's concave up and concave down, finding its critical points and its inflection points. If you have any questions, please leave them in the comments below, and if you have any other problems that you'd like me to do, please leave them down there as well. So let's get started. So finding the intervals of increase and decrease for a function is something that the first derivative does. The first derivative also helps you to find the critical points. So we're going to do both of those things first. We're going to find the first derivative first, and then find those places. So the first thing we're going to do is find the derivative. So f prime of x is equal to, and this is just the power rule, 1/3 x raised to the negative 2/3, because it's x to the 1/3, 1/3 minus 1, minus, bring the 4/3 down front and multiply by the 2, so minus 8/3 times x to the 4/3 minus 1, which is 1/3. So what I want to know now is where is this function where's the derivative undefined or equal to 0? Those are the candidates for the critical points. So a critical point is a point on a function where the derivative is either undefined or 0, but the function exists at that x value. So we're going to ask, where is f prime of x undefined or 0? Okay, so just by looking now, I know that the derivative is going to be undefined when x is equal to 0, because I have this x to the negative 2/3. And if that's 0, then that's going to be a problem. So f prime of x is equal to 0, is undefined at x equals 0. So now let's take f prime and set it equal to 0. So we'll take 1/3 x to the negative 2/3 minus 8/3 x to the 1/3, and we'll set that equal to 0. So I'm going to take and multiply both sides by x to the 2/3. And this is okay because I already know that x to the 0, or when x is equal to 0, that the derivative is going to be undefined. So I've taken care of that. And if I multiply by x to the 2/3, I get 1/3 minus 8/3 times x equals 0. And if I solve this for x, so I get 1/3 is equal to 8/3 x, multiply both sides by 3/8, and that tells me that f prime is equal to 0 when x is equal to 1/8. So our critical points are going to be at x equals 0 and x equals 1/8. So with those critical points, I can now find my intervals of increasing and decreasing. The best way to do that is to draw a number line. Draw a number line, and then you put down where the critical points are. So 0 and 1/8. Those separate the number line into regions that we're going to pull numbers from to test in the derivative. So remember that f prime of x is equal to 1/3 x to the negative 2/3 minus 8/3 times x to the 1/3. And our task now is to figure out what is the sign of the derivative in each of those regions. So let's take a value like -1. So -1 here is to the left of 0. And if I plug -1 in, f prime of -1 is equal to, well, -1 to the negative 2/3 is going to be +1. So it's 1/3 times 1 is 1/3. And then -1/3 to the -1 to the 1/3 is also -1. Multiply that by -8/3, I get +8/3. So I get 1/3 plus 8/3, which is going to give me 9/3, which is 3, which means that this region is going to be positive. Let's take another number, like, let's see, that's an easy cube. It's between 0 and 1, but 1/27th. So if I put 1/27ths in there, I get 1/3 times 1/27ths to the negative 2/3 minus 8/3 times 1/27ths to the 1/3. So 1/3 times, and then the negative is going to flip that over. So that's 27 raised to the 2/3. The cube root of 27 is 3, squared is 9, minus 8/3 times 1/27th to the 3/3. So that's going to be 1/3 there. So it's going to be 3 minus 8/9, which is positive. Doesn't really even matter what it is. 27/9 minus 8/9, that's 19/9. So that's going to be positive. So lastly, we'll take 1. And f of 1 now is going to be negative, because that's going to be 1/3 times 1 minus 8/3 times 1, which is negative 7/3. So that region right there is negative. So then that tells us now that the intervals of increasing go from negative infinity to 0. We have to stop at 0 because there's an asymptote there. And then we'll union that with 0 to 1/8. And then it's decreasing from 1/8 to positive infinity. Now for the critical points, we need to plug in 0 and 1/8 into our original function. So if we want a point, those have got to go back into our original function. So f of 0, well, that's just going to be 0. I've come back up and look at our equation. We get x to the 1/3 minus 2 times x to the 4/3. So both those x's are 0, then that function is 0. So now let's look at f of 1/8. So it's going to be 1/8 to the 1/3 minus 2 times 1/8 to the 4/3. So 1/8 to the 1/3, that's going to be 1/2 minus 2 times, so we have 1/2, the cubed root of 1/8 is 1/2. 1/2 raised to the 4th is 1/16. So 2 times 1/16. So that's equal to 1/2 minus 1/8, which is equal to, that's 4/8 minus 1/8, so it's equal to 3/8. So that tells me now that my critical points, move this out of the way, my critical points are at 0, 0 and at 1/8, 3/8. Okay, so now we get to wash, rinse, repeat for the intervals of concavity, where it's concave up and concave down. So let's find the second derivative. So bring the negative 2/3 down front and multiply by 1/3. So we get negative 2/9 times x to the negative 2/3 minus 3/3. So it's going to be negative 5/3 minus 8/3 times 1/3, which is 8/9 times x to the negative 2/3. Okay, so like we did before, f double prime of x is undefined at x equals 0. And that's fine. 0 can go into the original function, and so that's going to be one of our inflection points. So let's now set the second derivative equal to 0. So we get negative 2/9 times x to the negative 5/3 minus 8/9 x to the negative 2/3 equals 0. So again, I'm going to multiply everything by x to the 5/3. That'll get rid of the negative 5/3 and make the negative 2/3 positive. So get negative 2/9 minus 8/9 times x equals 0. So if I solve that, we get negative 2/9 equals 8/9 x. And then divide both sides or multiply both sides by 9/8, and we're going to get x is equal to negative 1/4. So f double prime of x equals 0 at x equals 1, negative 1/4. Okay, so now we're going to use another number line to help us determine where the intervals are of concave up and concave down. Okay, so once again, we're going to draw a number line. And we'll put in our values. So we've got 0, and we've got negative 1/4. So just like we did before, we're going to separate these into sections here, and we'll choose negative 1 for our first value. Now if we plug in negative 1 into the second derivative, the negative is going to stay. So we'll get positive 2/9 plus 8/3, and that's going to end up being end up being a positive value. Change some of my mistakes here. There we go. So that's positive there. And if we take a number that has an easy cubed root, something like negative 1/8, and we plug that in, then let's see what we get. Okay, so plugging in negative 1/8 gives us a positive 3 5/9. So that's going to give us a positive number. And let's take and plug in 1. If we plug in 1, those negatives don't go away. So it's minus 2/9, minus 8/9, and that gives us a negative number. So now we can come up with the intervals of concavity. So we are concave up wherever the second derivative is positive. So that's going to be from negative infinity to negative 1/4. And then we'll union that with negative 1/4 to 0. We're concave down where the second derivative is negative. So that's just going to be from 0 to infinity. And then our inflection points, well, we need to know what happens when you plug 0 in to our function. And we also need to know what happens when we plug in negative 1/4 into our function. 0 is easy. It just becomes 0. Negative 1/4, we'll take that negative 1/4 and we'll raise that to the 1/3 power. And then subtract away 2 times negative 1/4 raised to the 4/3 power. And we can get a number for this. It's not going to be a very nice number because the cube root of 1/4 isn't going to be rational. So we might just leave it at this. So, or we can take out a negative 1/4 to the 1/3, and then we'll get 1 minus 2 times negative 1/4 here. And so that's going to be negative 1/4 raised to the 1/3 times 1 minus, or 1 plus 2/4. So it's going to be 3/2. So our inflection points then are the points 0, 0, and the point negative 1/4, comma, negative 1/4 to the 1/3 times 3/2. Okay, so now we can draw everything out. So we'll get a coordinate plane here, and we'll put in our key numbers here. So we know we've got something at 0, 0, and then there's negative 1/4, and then this will be 1/8 right here. So looking back at our critical points, over here we're told that 1/8 is at 3/8, and then negative 1/4 is at negative 1/4 to the 1/3 times 3/2. So that's going to be somewhere around 1/2 here, negative 1/2. So somewhere down here like this. Okay. So the only thing left to really find is the place where x to the 1/3 minus 2x to the 4/3 is equal to 0. And we could We could go ahead and set that equal to 0 to find the zeros. So the zeros are where x to the 1/3 minus 2x to the 4/3 is equal to 0. So I'm going to pull out an x to the 1/3, and we get 1 minus 2x equals 0. So when x is equal to 0 or to 1/2, then we're going to have a 0 for our function, which we kind of already knew. So 1/2 is down here, and right there. Okay. So looking back at our intervals of increasing and decreasing, we know we're increasing from -infinity to 0, and then from 0 to 1/8. So that 0 is going to be at positive 1/2, not negative 1/2. So let's put that over here. So the function is increasing all the way to 0. So that means it's going to start from the bottom here, and it's going to come all the way up to here. And now the derivative is going to be undefined. So that means that it's going to be vertical right there. And we're also told that at -1/4, that's going to be a change in inflection. So we're going to be concave up or concave down, and then we're going to be concave up. If you go back and look at your chart, actually, this should be concave up here rather than concave down. So it's going to be kind of like this, and then we're going to come over to the spot at the origin where we're going to have a vertical tangent, and then at that vertical tangent, then we're going to go to concave down, and then we know at 1/8 we're going to reach a horizontal tangent, and then we're aimed for 1/2 here, and we're still going down. We're still concave down all the way. So you can verify that sketch with Desmos, but that is it. And I appreciate your watching this video. And thank you very much, and we'll see you in the next video.